Hi everyone, welcome back to P5. In P5, we're going to change gears a little bit and start talking about rational expressions. In the past, we've talked about rational numbers, so rational expressions aren't going to be super different, but different enough that we have to dedicate its own section. Okay, so if rational numbers are numbers of the form a over b where b can't equal 0, then rational expressions are, believe it or not, expressions of the form a over b, where b does not equal 0. So in general, when we're talking about rational numbers, right, the numerator and denominator are just numbers. But in rational expressions, the numerator and denominator can technically be anything. They can have absolute values, they can have square roots, they can have all sorts of weird things. But for the purpose of what we're trying to do in this section, the numerators and denominators are going to be just polynomials for this section. But again, they can be anything. The domain for a rational expression is the set of all values where the denominator does not equal 0, right? If we want an expression to be defined, we need to make sure that the denominator does not equal 0. So for example, the domain of 2 over x minus 1 would be everywhere that x does not equal 1, because if we plug in 1, 1 minus 1 is 0, 2 over 0 is undefined. So the set that it is defined, the domain is everywhere except 1. And we're going to spend a lot more time doing this when we get to chapter 2, but at least we're setting the stage right now. Similarly, x plus 6 over x minus 3 times x plus 4, the set of all x values for which this expression is defined, would be everywhere except 3, right? If we plug in 3, 3 minus 3 is 0, 0 times anything is 0, and also when x does not equal negative 4. Negative 4 plus 4 is 0. 0 times anything would be 0. So they are defined everywhere except those two places. But again, we'll come back to that in chapter 2. To simplify rational expressions, first what we're going to do is separately factor the numerator and denominator. Don't try and do too much at once. Factor the numerator, factor the denominator, and then divide out anything that the numerator and denominator have in common. So this is just like canceling out common factors, just like we did for numbers back in P1. So let's get right to it. X to the fourth plus 2x cubed over x plus 2. I'm going to have some of these disclaimers here, like if x doesn't equal 2, right? Because we don't want x to equal negative 2 here. But, at some point I'm going to drop them. And we can just assume that we want this to be defined everywhere. So x to the fourth plus 2x cubed over x plus 2. What we're going to do is factor as much as we can and see if anything cancels out. Well, you might notice that in the numerator, they have an x cubed in common, so let's factor out x cubed. And right away, you see the numerator has an x plus 2 and the denominator has an x plus 2. So we can cancel out x plus 2. And one thing I want to note is that we can only cancel out factors. Factors are things that are being multiplied together. So this is x cubed times x plus 2. X plus 2 is a factor itself. X plus 2 in the denominator is a factor itself. So we're canceling the entire factor, right? If these were just numbers, we can't cancel things out that are being added or subtracted, but we can cancel out these multiplied and divided terms. That's very important. Okay, then, x cubed over 1, just x cubed. So let me ask you, would you rather plug something into this original expression or into just x cubed? That's the goal of simplifying rational expressions. X squared minus x minus 6 over x cubed minus 3x squared. Well, we see the numerator can be factored using AC method. What two numbers multiply to negative 6 but add to negative 3? And in the denominator, we can factor out an x squared. So what two factors of negative 6 add to negative 1? Negative 3 and positive 2. And now you see x minus 3 times x plus 2 over x squared times x minus 3. X minus 3s can cancel out. And x plus 2 over x squared, perfect. And this is again where I want to stress that we can't cancel things out that are added or subtracted. Notice here you might be tempted to cancel out an x and an x squared, but we can't do that because this x has to be added to 2 first. So do not cancel things out that are being added or subtracted. Cancel things out that are being multiplied, right? Like here, x minus 3 is being multiplied by x plus 2, and x squared is being multiplied by x minus 3. Cancel out things that are multiplied and divided. not added or subtracted. Okay, x to the fourth minus 9x squared over x to the fifth plus 6x to the fourth plus 9x cubed. Great practice from P4, but in the numerator, we can factor out an x squared. In the denominator, all of them have an x cubed, so let's factor out x squared and x cubed. Well, x squared minus 9 is a difference of squares. X squared minus 9 would be x plus 3, x minus 3, right? A squared minus b squared is a plus b, a minus b. And x squared plus 6x plus 9, what two factors of 9 add to 6? Well, 3 and 3. So again, x squared minus 9, difference of squares, a plus b, a minus b. And then the denominator, x plus 3, x plus 3, would be x squared plus 6x plus 9. And now let's see some of the things that we can cancel out. Well, right away, you see an x plus 3 can cancel out. There's 1 in the numerator and 2 in the denominator. We can only cancel out one of them. And then we have x squared over x cubed. We have 2x's up here, 3x's down here. We can cancel out 2 of them. So we're left with just a single x from that x squared over x cubed. X minus 3 stays. The other x plus 3 stays. This, very beautiful. X minus 3 over x times x plus 3. Okay, so basic simplification isn't very exciting, but just like we were able to do for polynomials and for fractions, what we want to be able to do is add, subtract, multiply, divide. But at least the benefit here is that multiplication, division, addition, subtraction, all exactly like how we did it for fractions, except the only difference now is that we're introducing x's. So multiplication and division is just like fraction multiplication and division. Multiply the numerators across and multiply the denominators across. However, I want to stress this. Oh, and before that, division is keep, change, flip, just like it was for numbers. However, before you do any operations, including addition and subtraction, right? This subsection is for multiplication and division, but for doing any operations, please factor your numerators and denominators first. We want to be able to cancel things out, but if you multiply and extend all these crazy things, what's going to happen is you're going to get some really, really crazy things that you're not going to be able to factor afterwards. So please factor before you do anything else. So x squared plus 3x plus 2 over x cubed plus 3x times 2x cubed plus 6x over x squared plus x minus 2. All right, 4 different things we need to factor. Let's get right into it. X squared plus 3x plus 2. What two factors of 2 add to 3? 2 and 1. So this will be x plus 2, x plus 1. X cubed plus 3x. They both have an x in common. Factor out an x. 2x cubed plus 6x. They both have a 2 in common, and they have a single x in common, so factor out 2x. And the denominator here, what two factors of negative 2 add to positive 1? Positive 2 and negative 1. So I'm skipping a lot of the factoring stuff. If you need to practice factoring, go back to P4. But here we go. Everything all nice and factored. Now, multiplication for rational expressions just says exactly like it did for regular fractions. Multiply the numerators across, multiply the denominators across. Okay, so x plus 2 times x plus 1 times 2x times x squared plus 3, x times x squared plus 3 times x plus 2 times x minus 1. And this is where our job is nice and pretty. If you had tried to multiply these numerators, you would be getting an x to the fifth term, a lot of different terms that you wouldn't know how to factor in the end. But since we factored to begin with, you might notice x plus 2 can cancel out, x squared plus 3 can cancel out, and a single x can cancel out. So x plus 2 went away, x went away, and x squared plus 3 went away. All we were left with is x plus 1 times 2, and this x minus 1 down here. And just to finish up, these single factors, we like to put them in front, just so it looks a little bit prettier. Do not go back and redistribute this 2. If you redistribute the 2, you went backwards, it's not fully factored, right? Our job is done when we are fully factored. Okay. 3x squared minus 24x plus 36 divided by 7x squared minus 28 divided by 9x minus 54 over 7x squared plus 63x plus 98. Oh my goodness. All right. Again, factor first. Don't do anything else besides factoring first. Okay. Up here, all of these are divisible by 3. Let's factor out a 3. Both of these are divisible by 7. Let's factor out 7. Both of these divisible by 9. Factor out 9. All of these divisible by 7. Factor out 7. Here, AC method, what two numbers of positive 12 add to negative 8, negative 6, and negative 2? X squared minus 4, difference of squares, x plus 2x minus 2, x squared plus 9x plus 14, x plus 2, x plus 7, right? What two factors of 14 add to 9? X plus 7 and x plus 2. Okay, fully factored. Now let's go for the operation. And just like division for regular fractions, division for rational expressions is the same. Keep, change, flip. Keep the first, change the sign, flip the second. And now let's multiply across. Just combine all the numerators and denominators, and let's see what can cancel out. Well, x minus 6 can cancel out. X minus 2 can cancel out. A 7 can cancel out. And an x plus 2 can also cancel out. So that's a lot that canceled out. We're left with just a 3 and an x plus 7 in the numerator. And then we're left with just a 9 in the denominator. And then 3 over 9 is 1/3. And we can drop the 1. We don't need to say 1 times. Okay. So I know we're skipping a lot of work for factoring, right? We assume previous section is good. So let's continue. Well, that was multiplication and division. Let's now do addition and subtraction. Well, just to very briefly reiterate the quirks and the quirks to fraction addition and subtraction, let's do some of these. So 1/5 plus 6/5, same denominator, just add the numerators. Same denominators, subtract the numerators. -4, 7 minus 11 is -4. -4 over 12, -1/3. 1/4 plus 1/8, when they don't have the same denominator, make them the same denominator. Well, we can get 4 to look like 8 by multiplying by 2 over 2. Again, we want to multiply by 2 over 2 because 2 over 2 is just 1. If we multiply by 1, we don't change anything. And then if we multiply 4 times 2, we get 8, and we don't need to change the other one. So we get 2/8 plus 1/8, 3/8. 7 over 6 minus 5 over 18. We can change this 6 to look like an 18 by multiplying it by 3 over 3. And then subtracting 5 over 18. 21 over 18 minus 5 over 18, 16 over 18. And we can simplify that, 8 over 9. So these should be kind of familiar. We did these toward the end of P1. 1/4 plus 1/6. Well, they're kind of similar, right? Here, this is a multiple of 2, and this is a multiple of 2. So their least common denominator is not just 4 times 6. We can get both of them to look like 12. All right, 3/12 plus 2/12, 5/12. 1/3 and 1/8. Well, we can't say the same about 1/3 and 1/8 like we did for 1/4 and 1/6. 3 and 8 don't have any, early multiples in common like 4 and 6 do. So here, let's do 3 times 8 to get to 24. That's the first multiple that they share. 8 over 24 minus 3 over 24, 5 over 24. If we wanted to add all three of them together, well, 3, 4, and 5 don't share any factors. So if we want to get all the denominators to look the same, we got to multiply this one by 4 and 5, this one by 3 and 5, this one by 3 and 4. And we just get all sorts of ugly numbers. But the idea is here, right? If they have some similar factors, the least common denominator is not just all of the denominators together. It might be in some cases like 1/3 and 1/8, but it doesn't always have to be. So addition and subtraction, if the denominators are the same, simply add or subtract the numerators and keep the denominators the same. Okay, well, x minus 6 over x plus 1 squared minus x plus 8 over x plus 1 squared. Okay, Well, we are subtracting across, but be very careful. This isn't like numbers. When this is like numbers, we just subtract those numbers. But when we're subtracting expressions, make sure you're subtracting this entire expression. Please use parentheses. They are free. Okay, so x minus 6 minus the whole of x plus 8. Let's distribute a negative sign to each term. X minus x goes away. Minus 6 minus 8, negative 14. Not the biggest leap that we have seen so far. Well, what we're more interested in doing is when the denominators are not the same. So we're going to make them the same. Think about when we had 1/3 and 1/8. Those factors had nothing in common. So we needed to multiply 3 by 8, and we needed to multiply 8 by 3. And that's going to be more likely of what's going to happen in a lot of these cases. Look at x plus 1 and look at x plus 3. Well, they look very similar as factors, but they're not quite the same thing, right? They both have an x, so you want to say that x is a least common denominator, but it's not. Remember that x plus 1 is a factor itself, and x plus 3 is a different factor itself. So x plus 1 and x plus 3, more likely than not, don't share anything in common. For example, if x were to equal 2, this would be 2 plus 1, which is 3. This would be 2 plus 3, which is 5. And 3 and 5 as denominators don't have anything in common. So what we're going to do is say the least common denominator between these two things is just this thing times this thing. So if we want to get our denominators to be the same, this x plus 1 denominator needs an x plus 3. And just like when we multiply numbers by 2 over 2 or 8 over 8, we need to multiply by x plus 3 over x plus 3, right? X plus 3 over x plus 3. So long as x doesn't equal negative 3, this is just 1. Algebra is a lot of adding 0 and multiplying by 1. Okay, likewise, so we have x plus 1 times x plus 3. That's great. That means that x plus 3 is going to need an x plus 1. Okay, so let's multiply everything across. Not everything across. Let's multiply these sets across, right? These are being added, so multiply those, not those highlighted, hold on. Oop. Multiply those across and multiply the first two across. Okay, x times x plus 3 is just x times x plus 3. X plus 1 times x plus 3 is just x plus 1 times x plus 3. Don't expand any of these things necessarily, right? If you were to expand the denominator, it's going to change to something expanded that you could refactor. 2x minus 1 times x plus 1 over x plus 3 times x plus 1. And now these denominators are the same. They look a little different, but don't forget, a times b is the same as b times a. Okay, same denominator, we can add across. X times x plus 3 plus 2x minus 1 times x plus 1. From here, all we're going to do is expand, distribute x to each term, FOIL out these two, and from here, combine like terms. So we've been combining like terms since P3. Not going to spend too much time going over that here, but now you get the idea. Okay, we keep going. X plus 1 over x squared minus x minus 6 plus 2x minus 13 over x squared minus 9. Now, based on the previous example, what you are tempted to do is say, oh, these two things, nothing alike. Least common denominator is x squared minus x minus 6, and this one, x squared minus 9. Well, not quite, because don't forget the very first rule to doing all rational expression operations, and that is to factor. What two factors of negative 6 add to negative 1? There we go. Negative 3 and 2. X squared minus 9. Difference of squares. Okay. Well, now let's take a deeper dive into what the least common denominator would be. Well, they both have an x minus 3. So we don't need to multiply one or both by x minus 3 because they both already have it. However, this denominator has an x plus 3, and this one doesn't have an x plus 3. So if we want to get the denominators to be the same, we need to multiply this first one by x plus 3 over x plus 3. Likewise, this first term has an x plus 2 in the denominator, and this doesn't have any x plus 2. So we need to multiply the second one by x plus 2 over x plus 2. From here, we'll multiply across in each specific term. Well, even though the denominators look very different, right? These three things, multiplication is commutative, even though they're out of order. Multiplication, order doesn't matter. So the denominators are the same. We can add the numerators, and from here, expand, FOIL, combine like terms. Okay, nice. We keep going. X plus 4 over x times x minus 1 squared times x plus 2 plus 2x plus 7 over 4x squared times x plus 2 to the third. All right, there's a lot going on here. Let's again look at each denominator and say, oh, this one has this and this one doesn't have this, and make connections. Okay, well, x minus 1 squared times x plus 2. Let's look at the other denominator and see what it has and what it doesn't have. Okay, well, there's no 4 in front, so we got to multiply this by 4. We have a single x, but this one has two x's, so this one needs another x. This one has a single x plus 2, but this one has 3x plus 2's. So we need to multiply by 4 to get a 4. We need to multiply by another x to get x squared. And we need to multiply by 2 more x plus 2's to get to x plus 2 cubed. So 4x, x plus 2 squared. And now in this denominator, let's see what we're missing. Well, this has the 1 in front. Well, we have the 4 already, so we're good there. This has 1x, but we already have 2 x's. We don't need to add any more x's. This one doesn't have any x minus 1's, right? Over here, no x minus 1's, but this one has 2 of them. So we need to multiply by at least x minus 1 squared. This one has x plus 2 cubed, but we already took care of that x plus 2 cubed before. So we have now all of these denominators the same. When we rearrange our terms, even though they are, sorry, we rearrange the terms, and now we know that those denominators are the same. So we just add the numerators across. And for as ugly as it is, yeah, you're not going to get numbers this bad in almost any scenario. Even if you're not in my class or using this textbook, very rarely will you get rational expressions that are going to be this bad. So there we go. But yes, the key here is, what is this denominator missing that the other denominators have? What is this denominator missing that the other ones have? So kind of puzzle together until you get to a point where the denominators are the same. Okay, x plus 2 over x squared minus x minus 3x over 4 times x minus 1 squared. Again, step 1, make sure we factor first. Okay, what does this denominator not have that this one does? Well, this one doesn't have a 4 out in front, so we need to multiply by a 4. This one's got an x, this one doesn't, so we'll worry about that x later. But this one has a single x minus 1, and we need 2 of them. So let's multiply by 4 times x minus 1. We need the 4, and we need an extra x minus 1. Over here, well, the 4 is already there that we needed. This one already has 2 x minus 1's. Well, we don't need to add any more. But this one has an x, a single x variable. This one does not have that outside x. So just multiply by x over x. Multiply the numerators. Oh, sorry, multiply numerators and denominators across in each term. They now have the same denominator, so we can combine them. And now combine like FOIL, sorry, distribute and combine like terms. Okay. X minus 2 over 2x plus 1 minus x over 2x minus 1. Well, they look very similar, those denominators, don't they? 2x plus 1 and 2x minus 1. But don't forget, even though they look similar, they are not the same factors. For example, imagine that x is 2. 2 times 2 is 4. 4 plus 1 is 5. 2 times 2 is 4, but 4 minus 1 is 3. So if x is 2, this denominator is 5, and this denominator is 3. 3 and 5 don't have anything in common. So even though they look alike, 2x plus 1 is very different from 2x minus 1. So this denominator is missing 2x minus 1. This denominator is missing 2x plus 1. Combine. They have the same denominator, so we can subtract, FOIL, and distribute, and just combine like terms. If you combine like terms and you get down to this is pretty good, but we can take one more step in factoring. We're very comfortable doing that. They both have a 2 in common. We can factor out a 2. So you already see that these get kind of messy. It's just the nature of the game. Alrighty. 14x over 3x minus 1 squared minus 2x plus 7 over 9x squared minus 1. Again, let's factor fully. 9x squared minus 1, that's a difference of squares. 3x squared minus 1 squared, so we can factor 9x squared minus 1 as 3x plus 1 times 3x minus 1. Okay, this denominator has no 3x plus 1s, so the first denominator needs a 3x plus 1. However, this one already has two 3x minus 1s, and this one only has one of them, so this denominator will need another 3x minus 1. Okay, combine, subtract, and FOIL, combine like terms, do whatever you need to do from there. Not necessarily the prettiest things on the planet, but that's okay. Okay, so addition, subtraction can get kind of messy. For the questions I'm going to ask you, they're not going to be nearly as messy, and I don't think almost any instructor will ask questions so messy. So yeah, but still, so long as you see like, oh, this one's missing this denominator, this one's missing this denominator, what it ends up boiling down to is just foiling and distributing and combining like terms. Okay, now complex expressions. It's better when we are in person talking about these things, because we can make some really, really messy looking rational expressions. But for now, let's just go over one example just so you kind of see the need to be careful aspect to it. So for complex expressions, just work as careful as possible. Simplify your simple parts first, work your way harder and harder, but start with the easy things. And then, work your way up to the bigger stuff. So let's say we have 1/2 plus 1 over x squared minus 4 over 2x. Well, in the numerator, we can combine terms here. If this was, first of all, find the least common denominator. So 2 times x, we got 2 times x over x. This one needs a 2, so 2 over 2. X squared minus 4, x plus 2 over x minus 2. Well, in the numerator, let's combine that. Okay, well, now this is a fraction divided by another fraction. Well, that's just keep, change, flip. Let's multiply across, and now you see, 2x can cancel out, and x plus 2 can cancel out. So being very careful, taking care of the numerator separately from the denominator, putting it all back, small stuff like that. But the bulk of this section is the multiplication, division, addition, subtraction, more especially the addition, subtraction. So something to keep an eye on. Okay, that's all I got for P5. So practice the addition and subtraction. But we got one more section in chapter P. So I will see you in P6. Bye-bye. Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leslavska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.